I did want to add when Kellen talked about power outages in Marin County being a primary consideration, I had a very visceral reaction because I still remember from a few years back when we had an extended power outage, and my wife took our kids and went to Petaluma to her parents' house and left me there, and the fridge went out and I had no food and I got really, really hungry. And I remember finally a cafe opened and I got a panini, but they couldn't grill it. So I still remember I was basically eating a ham sandwich with butter on the outside of the bread. Anyhow, I digress. Is my presentation up here?
Yeah.
Got it. Okay. So I have an architecture firm and I specialize in high performance modern homes. And the technical underpinning of that is passive house or passive building. And so I'm going to I don't know, I'm assuming many of you are familiar. I'll do a quick introduction to that and then talk about a couple examples and then a quick discussion of how code and passive house align and don't. So what is passive house? It's a rigorous building design and performance standard. It was formalized by European scientists around 1990, and it drew a lot on super insulation and passive solar work in the United States from the 70s, and also low energy building work in Europe following that. And it sort of turns everything on its head, in my opinion, and it defines the quality of a building by how little energy is required for comfort and convenience. And it offers superior comfort, indoor air quality, and durability. And there are tens of thousands of these worldwide at this point, not just single family, multifamily, commercial, institutional buildings. This was the world's first passive house. And so there was a German physicist who formalized this concept, and he actually still to this day, lives in his own experiment. So this is a 4-unit townhome basically, and he lives in the end unit. And I visited there in the wintertime, and what I was amazed by, very cold, but normally in cold climates, when you have multi-story buildings, it's cold on the bottom floor and you go to the top and you kind of get a nosebleed because it's hot and dry. And this was just uniformly comfortable from top to bottom. This was the first passive house in the United States, built in Urbana, Illinois. And this is the first passive house in California. And this is how I became acquainted with it. I was basically an architect who was living from California, moved to Austria, and then came back and retrofitted his bungalow in Berkeley to meet passive house standards. And this is the first certified passive house in California. And it was also the first certified passive house retrofit in the United States. And I had the honor of working on this. This is in downtown Sonoma, city of Sonoma. It's called the O'Neill Residence, if you want to look this up. Anyway, how does passive house work? Optimize solar gains so that particularly in a climate like this, not just getting solar gains in winter, but excluding them in summer. A draft-free building shell. Heat recovery ventilation is typically used. Continuous insulation, high performance windows and doors, efficient equipment, appliances, and lighting. And lastly, this is where it maybe gets a little weird, renewable energy at the end of the list. We'll talk a little bit more about that. Benefits of passive house: health, filtered 24/7 filtered fresh air. We've also been doing a lot of work with dealing with wildfire smoke in these buildings. Because you have control over the air entering the building, you have the opportunity to filter it. And we've found that adding supplemental HEPA filtration at the intake to the ventilation system, you don't want that there all the time because it ups the fan energy a lot. But if you can make that convenient to insert and remove, it's very effective during wildfire events and keeping the indoor air quality high. It's a durable shell, free of mold and moisture problems. In the wealth department, tiny energy bills, high quality construction. It's immune to changing energy prices and policy, And a thing I like to talk about is I view these buildings as thermal batteries that can store their heating and cooling. And we'll see some examples of that shortly. Happiness, safe, healthy home for the occupants and the planet, legacy buildings, quiet, secure, and comfortable interior. And I also refer these with my clients as sanctuaries in the modern world. I've been doing this since 2008. And I'm still, every time I go into one of them, I'm really taken by how quiet they are once you get inside, and with the doors and windows closed. If you want to hear birds chirp or cars go by, open the window, no problem. It's just that you can close them if you want. And this is based on 40 plus years of research and engineering, and there's 30 plus years of proven performance, monitored performance all over the world. And efficiency is a permanent gift, right? So if you make an efficient building, it's permanently efficient. This is a kind of a snapshot of projects that we've worked on since 2008, give or take. There are a few more in the works and a few more not on here, but we've been at it for quite a long time. Most of our projects kind of clustered in the Bay Area, but we're always looking to sort of stretch out and expand to the other 15 climate zones that we have. This is the first project I just wanted to examine. So this is the before. This is called Midori House in Santa Cruz. So it was a 1922 craftsman, and we remodeled and retrofitted it to passive house. That's the front view. This is, we talk about indoor outdoor living, not a very inviting connection to the backyard in the first place, but our remodel did a lot more to connect the occupants to the landscape. This is the existing floor plan and the revised floor plan, and the clients didn't want to expand, so we just kind of reconfigured and utilized the interior space, added decks to the outside, adjusted some of the glazing positions, and just made it kind of updated for modern living. And this is a detail of connection, basically re-sheathed the building, put 3¼ inches of exterior rock wool insulation on the outside. That's basically the wall. Took a lot of care to make sure it was air sealed, but not insane amounts of insulation or any materials like that. Likewise on the floor, the main exercise here was getting the air sealing done. And I heard from the contractors that crawling around in the crawl space doing that was not much fun. So you do what you got to do. This is an example again of this thermal storage idea, and this is a napkin sketch that I did at a conference, looking at kind of the concept. If we're trying to move towards storage, which we need for an intermittent renewable grid, on the right we can do an efficient building envelope where the building itself can be part of the storage, or on the left we can do a typical building envelope where we then pack it full of batteries to make up for the fact that it isn't efficient. And this is a bit of an exaggeration, but I predict this is going to happen. Oh yeah, and then the one on the left has to have the roof covered with solar panels to try to make this happen, including on the wrong side. So again, efficiency and storage, if the building itself can store its heating and cooling, it goes a long way. So here's an example again of Midori House, and this is in Santa Cruz, and it has no air conditioning, but they do have freak heat waves now and again. So their cooling is night cooling. Right? When it's evening, night, or early morning, they'll open the windows to let cool air in, and then they close the windows and doors to get through the day. There was a heat wave in May. Apparently these happened there. And it got up to 103 outside, and the warmest temperature during that day was 76 degrees inside, with no cooling whatsoever, with the ventilation system running as well. So even if you're in a climate that does require air conditioning, this kind of resiliency enables you to conveniently run your air conditioning. You don't need to run it at peak time. You can choose what time of the day or night to run it because the building itself can hold that temperature. Likewise, in the winter, it can hold the temperature. So you could choose a convenient time to run your heat pump, be it when the sun's out and the solar panels are running or whatever. It lets people adjust and decide when they condition their home, not be forced to follow peak conditions. In terms of seasonal demand, this is just a look at their electric and gas bills. And this building had, this was done in 2013. So it has a solar thermal system with a gas boiler backup. The solar thermal system or the hot water system of the house provides the hot water for the house and also provides the heating. But if you look on the right at the utility bill, I think what's most striking is the relative lack of peak through the year. You know, typical building on the right and the efficient ones, in winter, the gas use spikes, and this one's almost flat year round. So it's doing an excellent job of mitigating what will be the biggest challenge in an all renewable grid. Air conditioning is not the biggest problem, not even close, because you have solar at the time, even if it's a few hours removed. The hardest thing is providing power in winter because you need a lot of heating. And the reason you need a lot of heating is because there's not a lot of sun out. So solar doesn't help you heat because you need heat because there's not enough sun. You know, it's not an inconvenient situation. It's actually caused by that. Anyhow, the efficiency measures of this building, the fact that Passive House utilizes internal heat gains as well to help warm the building, enable it to get to these levels where there's still heating needed, but much, much flatter year round. And this is just looking at their actual energy use and comparing it to a typical house. This is another project in Sunnyvale in 2019, mid-century house that we remodeled and retrofit to Passive House. Again, not a terribly inviting rear facade. To get to the backyard, you had to go through a bedroom and out the side. And we changed it to this floor plan before and after. This one was expanded somewhat, but we basically kept largely to the same footprint, but kind of squared the building off and made it a lot more livable for the homeowners. Details of the floor on this one. We did a clean crawl space, so we reduced the vent openings to 1/10 of what they typically are in a standard code crawl space. Did the air sealing of the floor at the plywood deck, 7 1/4 inches of insulation, and move the water supply pipes into the joists so that they're actually inside the envelope rather than outside. The walls, just 2x4 walls with dense pack cellulose and 2.5 inches of surplus polyiso insulation. The contractor located a batch of it, I think, that had been taken off of a warehouse or something. And so they had a stack of that, used that on the outside of the walls. The walls were sheathed with zip sheathing, and that was the air sealing strategy for that. And the doors and windows are a European company that we use quite a bit, and they're at an R7 window as opposed to an Energy Star would be an R3, and it makes an enormous difference in the performance of the building shell. The roof, I kind of named this after the builder in Sonoma who I thought came up with this idea, but if you look at the truss, there's an extra parallel cord added to the truss, and that's strictly there just for stapling the netting of the dense packed insulation so that you can do dense packed cellulose easily up against the roof sheathing. And again, zip sheathing, the overhangs are actually attached after the air sealing. So we want to get a really good air seal from the roof sheathing to the wall sheathing. So the building ends up first starting with no overhangs at all, and then they're added on top, interspersed with the rigid insulation that we use to give us an unvented roof cavity. 12 inches of cellulose, and again, 2 inches of polyiso. And we also use cool or reflective roofing. Example here in the garage, just thinking through the air barrier situation, we actually, an attached garage, we did a split truss where the roof, even though the roof looks continuous, in this point it's actually split so that we could guarantee that we had wall sheathing connecting to the roof sheathing outside of the garage to keep that unconditioned space separate. And it's also good for indoor air quality. The shading details, we did 36-inch eaves, low solar gain glazing. This is the west side of the building that has a lot of glass, but there's a pergola on it with a shade cloth. It could also be done with plants. And then looking at the energy use. So the client decided that he didn't want to put his photovoltaic system up until he had a year of operation to size it. And then apparently had some difficulties with the fire department because they added Tesla power walls. And so there was some kind of back and forth for months over that. Anyway, the short and long of it was it didn't get fully grid interconnected until the beginning of this year. But this energy use I'd add is also including charging 2 EVs. So this is running an entire all electric house and providing their transportation. Before the remodel, they were spending about $150 a month, and their house would swing between 55 and 95 degrees, depending on the time of year, no car charging. After the remodel, before they put their solar on, they were spending $180 a month for a perfectly comfortable house and charging 2 electric cars. With the solar, first 3 months of the year, they averaged about a $20 a month electric bill. $11 of that was the connection fee. And then April was negative $67. So they already zeroed out the first 3 years of the month with April's solar surplus. And again, this is early on, but I predict it's going to be symmetrical about December. So it looks, I would say that September is going to take care, October will take care of, September will take care of October, November, December. So basically the building is off grid from May to August. So the poor guy actually oversized his solar system quite significantly. I think part of that is because he's got power walls in it, and that's enabling him to harvest a lot more than maybe the modeling would normally have. And the peak grid draw was 688 kilowatt hours. That was the highest month in December. Biggest draw with PV connected. And this was done with 8.5 kilowatts of PV and 2 power walls. And you can see that there was plenty of roof space left. And as I said, it's probably larger than needed for a net zero year-round performance. So these are aspects that I include in California for water, well, both water heating efficiency and water use, but this is a CO2 powered heat pump water heater. Drain water heat recovery we didn't do in this building. That typically requires 2 stories, but there are some units coming out that go in the floor of the bathroom for the shower, which we're exploring. Structured plumbing to deliver hot water quickly with minimal waste. Rainwater ready. So again, this is a standard thing we do. We just plumb the cold water laundry and all of the toilets with dedicated lines that all connect to an easily accessible point, and they'll connect to city water. But the point being, if somebody wants to either immediately or later implement a rainwater harvesting system, you don't have to tear the house apart. It doesn't cost much to do it when you're doing the construction. Later on, it becomes a big deal. Low water permeable landscape, and also gray water ready. So again, when we put the drains in, we organize those so that whether they have a gray water system implemented now or later, it's a matter of connecting that system. It's not a matter of installing the plumbing through the whole house. terms of air quality, this is a heat recovery ventilator, a Zender heat recovery ventilator, and it's basically a centralized ventilation system that continuously draws stale air from bathrooms and the kitchen and the laundry area out of the building and supplies filtered fresh air to all the other rooms. So you've kind of got this silent cycle of fresh air through the house. And as the air is being extracted, this thing's got a heat exchanger in it. So if it's, say, cool inside and hot outside, the air that you're taking out of the house will cool the air coming in. Vice versa in wintertime, if it's warm inside and cold outside, the warm air that you're taking out of the house will warm the air that comes in. So you're continuously turning over the air, but recycling or retaining the temperature of the building. And this is 80 to 90% efficient at that. Vented range hood with dampers, HEPA filter, again, a supplemental HEPA filter for a wildfire. And this is a look at 7-month-old filters in the heat recovery ventilator. So you can see what they didn't breathe that most of us do. And, you know, it's just a really nice house as well, which is important to me and them. I did how are we doing on time, by the way? Couple more minutes. So I'm going to get even faster now. And this will be available later, and I'm happy to answer follow-up questions. I know I just have so much to share, but this was a study I did, again, trying to expand uptake of this. I took California code and this is a prototype home from the energy modeling from Title 24 and upgraded it to passive house in all 16 climate zones. And the results look something like this. On the left side is the code, the same house built to code in each climate zone. And on the right is where our optimized buildings wound up. The big bump that you see in there is because I started out with a raised floor, and then I switched it to a slab on grade. And since code doesn't require any slab on under slab insulation, I ruined my house and then I fixed it again. And this is just a quick look at how many of these optimized buildings could be heated and cooled for the same amount of energy as the code house by climate zone. And just looked at, again, the most effective upgrade by location, and almost without fail, it was either under slab insulation or air tightness in every climate zone. That was the most effective upgrade available. I did add a couple more slides that will be in the PDF that have a little bit more data on this, but didn't get them in for this purposes of this. One thing I guess I wanted to say about code, it was tricky to compare passive house to code because code doesn't actually have a standard. It compares every building to itself, as opposed to passive house has an objective standard of this energy limit. So to compare it, I had to pick a particular house. I picked that prototype Title 24 house because code has a different number for every building in theory. And so this is kind of an example of the difference between performance and modeled compliance, and a little dated, but I think still effective. So this is a 2012 Yukon Denali that gets 21 miles per gallon, and this is a 2012 Honda Civic that gets 44 miles per gallon. And which of those is more efficient? The Honda, okay. And I need to add, because I've gotten this before, this is California, so it's one person driving in an hour to work each way. Okay, so there are the two, and the Honda's more efficient. But then we have a baseline, the non-hybrid Denali and the baseline Honda Civic. And if we look at the improvement over baseline, which one is more improved compared to its baseline, right? If you're merely comparing the building to itself, like code does, which of these two vehicles is more efficient? Exactly. So That's food for thought. And that's all I have to say. Thank you for your time.